Hey students, got a question from chapter 6, number 8 here. So let's kind of work through it. It's got 3 parts. It's also what they call an integrated concept. So I think it goes back to some other chapters. And so it doesn't just include this chapter, but past chapters. So when kicking a football, a kicker rotates his hip about the hip joint. So maybe it would look something like this. If this was kind of the hip joint and the leg comes down, and then here's kind of the foot. And so it's going to pivot, if you will. It's going to rotate along the length of the leg. And it says here, if the velocity of the tip of the kicker's shoe, so over here, has a velocity of 35 meters per second, and the hip joint here is 1.05 meters from the tip of the shoe, what is the shoe's tip angular velocity? Well, in chapter 6, section 1, they gave you a nice mathematical connection between the linear speed and the angular speed. And so maybe I should review that, but I'll just start by punching those numbers straight in. So this is 35 meters per second. And the radius is the length of the leg. And so if I grab my calculator here and go 35 divided by 1.05, it's going to bring it down just a little bit to 33.3. I guess the meters cancel off, and that's per second. But remember, a radian is just kind of a clarifier. We like to use it at times like this to say, okay, what units are we doing? And we're talking about this many radians. That's what we call radians, real numbers. So it's the foot would be moving 33 1/3 radians every second. And so, 1 radian is what, roughly 60 degrees. So a third of that, 20. So you're talking about maybe somewhere in the neighborhood of 20 degrees is how quickly the foot would be moving from an angular perspective. Now, in case you're wondering, your author had done this by saying, let's start with velocity and think about something going in a circle. So since velocity is distance divided by time, if you think about 1 revolution, that would be 2 pi r. And then the time, we often use this like capital T for period. And then if you group those together, what this is really saying is 1 full revolution in radians is 2 pi. So this is, an angular speed. This is the 2 pi radians in 1 period. So that is the omega. And so now if I bring the r to the other side, you get what your author derived for you, which is this equation that I just kind of plugged and chugged and got the answer here. Now, if I go into part B, it says the shoe is in contact with an initially stationary, keep that in mind, 0 speed, 1/2 kilogram football for 20 milliseconds. What is the average force exerted given that its velocity is going to leave then at 20 meters per second? So this is where I'm going to go back a chapter or two and say, look, force is, or net force is, mass times acceleration. And going back to even further, I believe it's chapter 2, acceleration is change in velocity over time taken, or at least average is if we don't do our calculus. And that's what they do say. They do say, what's average. So just kind of do a non-calculus problem, just in algebra. And now it's just, again, a matter of plug and chug in here, because this is a 1/2 kilogram. And the change in velocity is final at 20 and starting with being stationary, 0. And the time is the 20 milliseconds. And fortunately, they gave me some nice numbers to work with, because 20 divided by 20 goes away. 10 to the minus 3 becomes 1,000. 1,000 times 1/2 is 500. So we're looking at 500. And it should be newtons, and maybe I should check here. This would be a kilogram. This would be a meter per second. And then over a second, when I flip and multiply, makes kilogram meter per second squared, which is a newton. So 500 newtons would be, my answer for B. How much did I push on it? Yeah, it looks like I'll need another page here for C. And C says, find the maximum range. Now, again, this is kind of a review. We could go back to our projectile motions chapter, I want to say 3. But we had the range equation. We had the maximum range equation that said v squared over g. Now, maybe like part A, I should work that one out again. It would make a nice review. But this is hopefully, 20 squared and divided by g, which is 9.8. And we're looking here at about a 40.8 meters. And I got to admit, I'm kind of questioning myself if that's the maximum one. So why don't I go through this? I do remember this, though, that when you kick or throw something with a projectile, that as it takes off with some initial speed, call it v initial, and I guess I should have put v initial in that little formula, and the maximum occurs at a 45-degree angle. And so I'll take advantage of that and do what we used to do in these projectile ones, or what I encouraged you was to split your paper in two and write out an equation for the position of the object, in this case the football, as it moves along the x-axis, and then also write out an equation for the motion of the football in the y direction. And unless we have a reason to pick otherwise, it is very useful then to call the initial point the origin, so that these first two are zeros. In fact, maybe this would be a good time to review a little bit of our triangles. If we have something heading off at some initial speed and there's some angle theta, we can think of that as made a little bit in the x and a little bit in the y. In fact, why don't I call it an x and a y? Because if we do cosine theta of this little triangle, that gives us the x over this initial speed. And if I move that over, I get initial speed cosine theta tells me my x component of how fast it's going. That's why over here, for initial speed in the x direction, I'm going to put 20, and I'm going to put cosine of 45 degrees. Because we want to kick it at 45 degrees, and we're going to be kicking it at a speed of 20. Now, over here, kind of that same logic, if I did sine of theta, let's see, is that still on the screen? And I look at this triangle, it'd be opposite over hypotenuse, so that'd be the y component over the initial speed. And if I move that over, if I take initial speed, multiply it by sine theta, that tells me the y component. That tells me how much is it moving in the y direction. And that's what I want right here. So we don't want the whole speed of 20. This is just what is its initial speed in the x. So that's why we got to think about this initial speed, which is 20 at an angle, is actually a little bit to the right and a little bit up. So this little bit in the initial speed is 20 sine 45 degrees. Now let me make sure I include a t from the formula here, and then also the accelerations. And again, for projectile motion, we said gravity does not pull it, left or right, so there is no acceleration in the x, but gravity does pull it a negative 9.8 in the y direction. And now you see how we're going to get the range, and hopefully we're going to get the same thing as we got when we just kind of plugged and chugged, is we are going to say that if it starts here on the ground, and they said football, and I'm not sure if they meant American football or if they meant soccer, but I am going to imply that whatever it is, it starts on the ground and lands on the same level. And so my initial height is 0 and my final height is 0. And the reason that's nice here, blah, 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 is I can just put 0 equals, and I've got these things, where I can then factor out a t. And so 1/2 of 9.8 is 4.9 with a negative. And factoring out a t means I have no t here and a t there. But if remembering from our math classes, when two things multiply out to equal 0, either the first factor or the second factor equal 0. And in this case, when the first factor equals 0, time equals to 0, it's not a surprise that that's a solution, because at time equals to 0, the height would be 0. Yeah, that's when you're kicking it. So although that's true, it does solve for the correct time when the height is 0. It's not the one we want. So we must want this other one. And so 20 times the sine of 45 degrees equals, and I'll move it to the other side and then get my calculator. So 20 times sine of 45 and divide by 4.9, and we're looking at about 2.89 seconds. And then using that back over here, we can see where the x is, because this would be the 20, the cosine of 45, and now we got the time of 2.89 seconds. All right, so 20 times cosine 45, and then times the last answer. Oh, good. 40.8 is 40.8. So that would be kind of working it out from scratch in case we forgotten some of our maximum stuff. And that's fine. I think you should. That's kind of a special case. This is what you really want to have learned and remember long term is, how do you get how far it goes. All right. Hopefully that was helpful to some of you. Take care.